Look up. Beyond the familiar glow of our cities, beyond the veil of clouds, a silent, infinite theatre awaits its audience. It is a stage of impossible dimensions where the dramas are written in gravity and light, and the actors are worlds, stars, and the ghosts of creation. Tonight, and for the next few nights, we have been given a special invitation. It is not an event of human making. No tickets are required, no grand halls have been built. The summons comes from the deep past, carried across hundreds of millions of kilometers. It is a call to witness a celestial pilgrimage, a fleeting spectacle of fire and speed that connects our fleeting moment to the grand cyclical clockwork of the cosmos. This week, the Earth, in its own relentless journey around the sun, will plow through a river of invisible dust. This is no ordinary dust. It is the debris of a wandering giant, a ghost trail left by a comet named Tuttle. And as our world intersects this ancient stream, these tiny, forgotten particles of ice and rock will awaken. For one brilliant final moment, they will blaze across our heavens. This is the Leonid Meteor shower, a celestial appointment we have kept for centuries. It is a performance that promises not a deluge, but a delicate sprinkling of light. Perhaps 15 shooting stars each hour if you are patient. 15 incandescent whispers from the outer solar system. But to witness even one is to touch a story that began long before us, a narrative written in fire against the velvet blackness of the night. So how do you accept this cosmic invitation? How do you position yourself to catch these falling embers of a distant world? The first step is a retreat, an escape. You must turn your back on the modern world's luminous hum. The great enemy of starlight is our own manufactured glare. City lights create a dome of orange-hued pollution, a shroud that smothers all but the brightest celestial beacons. To truly see the Leonids, you must seek the profound primordial darkness. Find a place far from the luminous sprawl of civilization. Drive until the glow in your rearview mirror is a forgotten memory. Seek out a clearing, a hilltop, an open field, or a quiet lakeshore. The ideal location feels like stepping onto a different planet. The air grows crisp, carrying the scent of pine or damp earth. The silence is no longer an absence of noise, but a presence in itself, a deep, resonant quiet broken only by the rustle of unseen life or the whisper of the wind. Here, under a truly dark sky, the universe reveals its true texture. The Milky Way is not a faint smudge. It is a sprawling, incandescent river of light, a tapestry woven from a billion suns, so dense it seems you could reach out and touch it. This is your theatre. Now consider the timing. The performance has a schedule dictated by orbital mechanics. The peak of the shower, the moment of Earth's deepest passage through the cometary stream, occurs in the hours just before dawn. This might seem inconvenient, a difficult hour to keep, but there is a cosmic reason for this pre-dawn appointment. Imagine the Earth as a car driving down a highway at night. The front windshield accumulates far more insects than the rear. In the evening, we are on the trailing side of our planet, looking backward along our orbital path. But after midnight, our part of the world rotates to face forward. We are now on the front windshield of planet Earth, plunging headlong into the oncoming stream of Leonid particles. The meteors we see now are meeting us in a direct collision, making them faster, brighter, and more numerous. So set your alarm for the darkest hours. Give yourself at least an hour for the full experience. The first 20 minutes are for a crucial biological process, dark adaptation. Your eyes, accustomed to artificial light, must slowly recalibrate. The pupils widen, but more importantly, a chemical called rhodopsin, the pigment of night vision, must build up in your retinas. It is a gradual unveiling. At first, you see only the brightest stars. 5 minutes later, 1,000 more have emerged. After 20 minutes, the sky is a glittering cascade of diamond dust. You are now seeing with your primal eyes the eyes of your ancestors, and you are ready for the show to begin. What equipment do you need for this celestial viewing? The most wonderful answer is none at all. Your own two eyes are the most magnificent instruments for this task. Unlike a telescope which narrows your view to a tiny porthole, your naked eyes offer the grand panoramic vista the shower demands. A Leonid can appear anywhere in the sky. To confine your gaze to a small circle is to risk missing the main event. So bring a comfortable chair, one that reclines, or simply a thick blanket. Lie back and surrender your gaze to the entire celestial sphere. Let your focus soften. Do not search, simply watch. The most spectacular meteors often appear in your peripheral vision, streaks of impossible swiftness that your brain registers a split second after they've vanished. If you wish to enhance the view, a simple pair of binoculars can be a delightful companion. After a bright meteor blazes its path, it can sometimes leave behind a ghostly glowing trail. This is a persistent train, a shimmering column of ionized air that can linger for seconds or in rare cases even minutes. Through binoculars you can watch this ethereal smoke ring, twist and contort in the high-altitude winds of the upper atmosphere, a fading signature of a particle's fiery demise. And what of the radiant? You will hear astronomers speak of this point in the sky. They will tell you the shower radiates from the constellation Leo the Lion. This does not mean you should stare intently at that single spot. In fact, that is the one place you are least likely to see a long, dramatic streak. To understand this, we must turn to a familiar analogy. Imagine you are driving a car through a gentle snowstorm at night. The snowflakes are suspended in the air all around you. But as you move forward, an effect of perspective takes hold. The flakes directly in front of you seem to come from a single point far ahead, the vanishing point on the horizon. They appear to radiate outwards from this central location, streaking past your side windows as long parallel lines. You wouldn't stare at the point the snow seems to come from. You would look to the side to see the most impressive streaks. The Leonid Meteor shower works in precisely the same way. The particles are all moving in parallel paths through space like a vast cosmic flock of birds. As Earth travels through them, our perspective makes them appear to diverge from a single point in the sky located within the sickle-shaped head of Leo the Lion. This is their radiant. By tracing the path of a meteor backward, you will find it points toward Leo. This is how you confirm that what you saw was a Leonid and not a sporadic meteor or a traveler from a different shower. It is the shower's celestial address, its point of origin in our sky. To understand the true soul of this celestial event, we must journey back in time, not just centuries but millennia. We must travel to the source, to the parent of these fiery tears. Every Leonid particle that disintegrates in our atmosphere began its existence locked in the frozen heart of a comet. This particular progenitor is known as 55P. Tempel Tuttle. It is a relatively small celestial body, a nucleus of ice, dust and rock, perhaps only 3.5 kilometers across, a dirty snowball as they are so often called. For most of its life it is a dormant, silent traveler. Its vast elliptical orbit carries it on a 33-year journey from the relative warmth of the inner solar system near Earth's own path out to the frozen twilight realm beyond the orbit of Uranus. There, in the frigid darkness, it moves slowly, gathering its strength. Then gravity begins to pull it back inward on a long, accelerating fall toward the Sunday. As it crosses the orbits of Saturn and Jupiter, the Sun's influence grows. The frozen gases on its surface, water, carbon dioxide, methane, begin to stir. The closer it gets, the more intense the solar radiation becomes. The ice sublimates, turning directly from solid to gas, erupting from the nucleus in powerful jets. These geysers of vapor carry with them the dust and rock that have been trapped within the ice for billions of years. The comet grows a magnificent coma, a glowing atmosphere of gas and dust, and a tail pushed back by the solar wind that can stretch for millions of kilometers. Tempel Tuttle becomes a temporary spectacle in our skies, but it leaves something behind. Along its entire 33-year orbital path, it litters a trail of debris. Think of it not as a single object, but as a vast cosmic locomotive chugging along an immense invisible railway through the solar system. With each passage near the Sun, it lets out a great puff of cosmic soot. Over thousands of years, these puffs have spread out, creating a wide, clumpy river of particles that follows the comet's orbit. It is this river that Earth must ford every single November. Most years we pass through a sparse, evenly distributed section of the stream, and we are rewarded with a gentle shower of about 15 meteors per hour. But sometimes things are different. Sometimes Earth's orbit intersects with a dense, freshly laid clump of debris, a cloud of particles recently shed by the comet. When this happens, the gentle shower becomes a deluge, a celestial storm of unimaginable intensity. And it is these storms that have etched the Leonids into human history and legend. We must go to the year 1833. On the night of November 12th into the morning of the 13th, the inhabitants of North America awoke to a sight that defied belief. The stars were not just falling, they were pouring from the heavens. Contemporary accounts struggle to find the words. They speak of a sky filled with fiery darts of incessant flashes of light. One observer in Boston noted that the air seemed to be filled with stars, each leaving a long, luminous train behind it. Estimates later calculated by astronomers placed the rate at over 100,000 meteors per hour. For hours, the sky was a blizzard of light. This was not a subtle astronomical event. This was an apocalypse. Many believed it was the end of the world, the fulfillment of biblical prophecy. People fell to their knees in prayer. Others simply watched, paralyzed by a mixture of terror and awe. The sheer spectacle was so overwhelming that it seared itself into the cultural memory. It was the night the stars fell. But for a few curious minds, it was more than a divine portent. It was a puzzle. A Yale professor, Denison Olmsted, meticulously gathered eyewitness accounts from across the country. He noted two crucial facts. First, the meteors seemed to emanate from a single point in the constellation Leo. Second, the event was seen across the continent, proving it was not a local atmospheric phenomenon. Olmsted correctly deduced that this was an event of cosmic origin, a cloud of particles in space that the Earth had passed through. This single terrifying night gave birth to the science of meteor astronomy. The story, however, did not begin in 1833. Once astronomers understood the 33-year cycle of the parent comet, they began to search the historical archives. They found a breadcrumb trail of celestial fire stretching back through time. In 1799, the great naturalist and explorer Alexander von Humboldt, while camped in Cumana, Venezuela, witnessed a spectacular Leonid display. He wrote of thousands of shooting stars and fireballs that filled the sky for hours. Crucially, he spoke with locals who recalled a similar event decades earlier, leading him to wonder if it was a periodic phenomenon. Digging deeper, researchers found records from 902 AD, an event in Europe and Egypt described as the Year of the Stars. Chinese court astronomers, meticulous keepers of celestial events, had recorded Leonid storms with unnerving regularity. Each record was another link in the chain, another confirmation of this 33-year pulse of cosmic activity. The Leonids were not just a shower, they were a timepiece. The 20th century saw the legend rekindled. After a disappointing showing in 1866 and a near miss in 1899, Many thought the great storms were a thing of the past, that the dust streams had been perturbed by Jupiter's gravity and scattered. But on the night of November 17th, 1966, the Leonids returned with a vengeance. Observers in the western United States were treated to a spectacle that rivaled and perhaps even surpassed the 1833 storm. For a brief period of about an hour, the rate climbed to an astonishing degree. Not thousands per hour, but thousands per minute. Astronomers described it as being in a starship moving through a starfield. The sky was so full of motion that it induced a sense of vertigo. It was a waterfall of light, a silent, overwhelming torrent that left those who saw it speechless and forever changed. More recently, a series of lesser yet still magnificent outbursts occurred between 1999 and 2002. This time armed with powerful computers and a refined understanding of orbital dynamics, astronomers were able to predict where the densest dust trails would be. It was a triumph of science, turning a terrifying mystery into a predictable, if still awesome, celestial event. These events remind us that the river of debris is not uniform. It is a lumpy, braided stream, and our passage through it yields a different experience every single year. So what is it that we are actually witnessing in that split second of light? What is the physical process that transforms a cold, dark speck of dust into a brilliant incandescent streak? The journey begins with a meteoroid, the technical term for the particle in space. A typical Leonid meteoroid is staggeringly small. Most are no larger than a grain of sand. The brightest might be the size of a pebble. This is the first great paradox of the meteor shower, an object of insignificant mass producing such a magnificent effect. The key is not size but velocity. Leonid meteoroids are among the fastest of any major shower. Because they are traveling in a retrograde orbit nearly opposite to Earth's own direction, they slam into our atmosphere head-on. The combined closing speed is immense, about 71 kilometers per second. That's over 158,000 miles per hour. At such a velocity, a particle could cross the entire continental United States in under 2 minutes. It is this kinetic energy, the energy of motion, that is the source of the spectacle. As this hypervelocity particle enters the upper atmosphere around 100 kilometers above the ground, it encounters air molecules. At this altitude, the air is incredibly thin, a near vacuum by ground standards. But for an object moving so fast, it is like hitting a wall. A common misconception is that the streak is caused by friction. The reality is more violent and more fascinating. The process is called ablation, driven by something known as ram pressure. The particle is moving so fast that it cannot push the air molecules out of the way in time. Instead, it compresses the air in front of it into a pocket of incandescent plasma. This compression heats the air to thousands of degrees Celsius, hotter than the surface of the sun. This superheated pocket of air then vaporizes the meteoroid itself, stripping it away layer by layer, atom by atom. The sand grain or pebble is completely consumed in a fraction of a second. What we see as a shooting star is not the particle itself burning. It is the glowing column of air molecules and vaporized particle atoms that have been excited to a state of luminescence by the shock wave of its passage. We are witnessing the atmospheric tomb of a cosmic traveler. This process also gives the meteors their colors. The palette of a meteor shower is a lesson in celestial chemistry, a form of cosmic spectroscopy. The intense heat breaks down not only the particle, but also the molecules of the atmosphere. The dominant color is often a brilliant white or blue-green, a signature of superheated magnesium and iron from the meteoroid itself. Sometimes you might see flashes of yellow or orange, which is the telltale sign of sodium, just like in a streetlight. A reddish hue can come from excited nitrogen and oxygen molecules in our own atmosphere. Observing the color of a meteor is like reading its chemical fingerprint and the story of its interaction with our planet's airy shield. And what of sound? Occasionally, people who witness an exceptionally bright meteor, a fireball, report hearing a sound at the very same moment they see the light, a faint hissing, crackling, or popping noise. This has long been a mystery because sound travels far too slowly to reach the ground from 100 kilometers up in an instant. The phenomenon known as electrophonic hearing is now believed to be real. The theory is that the intense plasma trail of a very bright fireball emits a burst of very low-frequency VLF radio waves. These waves travel at the speed of light and can cause objects in the observer's immediate vicinity, like dry hair, glasses, or even grass, to vibrate slightly, creating a sound that is heard the instant the meteor is seen. It is a strange and wonderful example of the complex physics at play, a direct sensory connection to this distant fiery event. When you settle in to watch the Leonids, you are doing more than just observing a pretty light show. You are participating in a profound demonstration of our place within the solar system. This is not an abstract astronomical concept, it is a tangible physical interaction. Our planet is moving through the wreckage of another world. The dust that vaporizes in our sky is a physical relic, a piece of a comet that travels to the frigid edges of the solar system and returns. To see a Leonid is to have a direct encounter with that distant frozen realm. It collapses the immense scale of the solar system into a personal momentary flash of light. And the story is deeper still. Where did the dust in Comet Tempel Tuttle come from? It is primordial material, the leftover building blocks of our solar system. These particles of dust and ice were once part of the great nebular cloud of gas and dust that collapsed under gravity 4.6 billion years ago to form our Sun and all the planets. They are cosmic fossils, pristine samples of the material from which our Earth was made. For billions of years they were kept in a deep freeze in the comet's nucleus far from the Sun, preserving their ancient chemical composition. Now, after an eon in the dark, they are delivered to our doorstep, and in their final brilliant moment they offer us a fleeting glimpse into the dawn of our own world. Each fiery streak is the immolation of a tiny museum piece, a 4.6 billion-year-old artifact sacrificed for our momentary wonder. It is a reminder that we are made of the same star stuff, that the history of the cosmos is not just out there in the distance, but is falling into our atmosphere right above our heads. The 33-year cycle of the Leonid storms is a powerful lesson in the dynamic and interconnected nature of our celestial neighborhood. The comet's path is not fixed. The river of debris is constantly being shepherded and sculpted by the gravitational influence of the giant planets, especially Jupiter. The gas giant acts as a great cosmic gatekeeper. Its gravity can nudge the dust streams, sometimes pushing them into Earth's path, setting the stage for a great storm, and at other times pulling them away, leading to centuries of quiet showers. We are all passengers on this planet, moving through a celestial environment that is constantly shifting a web of invisible forces and ancient debris. What does the future hold for the Leonids? The great storms of the past, like 1833 and 1966, were the result of passing through dense filaments of dust shed by the comet in previous centuries. Current models suggest that the most concentrated of these streams have now been swept clean by Earth's passage or perturbed by Jupiter. We are unlikely to see a storm of that magnitude in the coming decades. The comet itself will return to the inner solar system around the year 2031, replenishing its trail with a fresh stream of dust. This might set the stage for enhanced activity in the years that follow, but the grand deluges of history may be on hold. But the universe is never entirely predictable. The Leonids will still return every single November. They will continue to offer their 15 meteors per hour, a gentle, reliable reminder of the comet's distant passage. And among them will be the occasional fireball, a brilliant flash of light that tears across the entire sky, casting fleeting shadows on the ground below, leaving a gasp in its wake. These are the moments that make the cold and the late hour worthwhile. So this week, step outside. Find that patch of darkness. Allow yourself the time to let the universe unfold above you. Feel the cool night air on your face and listen to the profound silence. Cast your gaze upward, not with expectation but with patience. You are not merely looking for lights in the sky. You are waiting for a connection to the deep past of our solar system, a connection to the astronomers and the ancestors who stood under these same skies and felt the same sense of wonder and humility. Each streak of light is a story's end and a moment of discovery. It is a grain of sand from another world becoming a part of our own. It is a silent, fleeting testament to the grand, intricate, and violent beauty of the cosmos. It is a personal message delivered across the void at impossible speed, reminding us that we are inhabitants of a living, breathing solar system, a place of constant change and breathtaking surprises. The Leonids are calling. All you have to do is look up and listen to the fire.